we said that we can express the configuration space, write it out in coordinates. And when you write it out in coordinates, you start to get a sense for the number of degrees of freedom. Degrees of freedom. Degrees of freedom of the system. So by example, a single elevator has 1 degree of freedom. You need a single number to describe its position. 2 independently controlled elevators have 2 degrees of freedom. You need 2 numbers to describe it. What about the funicular? How many degrees of freedom does it have? Well, it has 2 cars, so you might be tempted to say it has 2 degrees of freedom. How many people say, yeah, it has 2 degrees of freedom? How many people say maybe it doesn't have 2 degrees of freedom? All right. Can you give me a sense? What's your name? Yeah. No, I was asking you right here. No, I will walk up and point again. Yeah, right here. What's your name? Xing. Xing. Yeah, can you give me a sense of why it might not have 2 degrees of freedom?
It just has 1 degree of freedom. Q1 plus Q2, the sum.
There you go. So Xing said, once you know Q1, you already know you can solve for Q2 because the sum is equal to a constant. So you can't set, they're not both free variables. And pictorially, you can see this too. If you can move around anywhere in this 2D space, you have 2 degrees of freedom. But if you're restricted to moving only forward and backward along a 1D line, doesn't matter if the line is horizontal or vertical or diagonal, if you can only move forward and backward, you have 1 degree of freedom. All right? So a natural question comes up, how many degrees of freedom does this chalk have? Okay, I heard 3 and 6. So how many people say 3? 3, I have 1 3, 1 brave 3. How many people say 6? I have some brave 6s. I have a lot of people not answering. Any other numbers? 5? So this is a great question, right? So why are we puzzling over this? What would be the first 3 that would be straightforward? What's your name?
Aditya.
Again?
Aditya.
Aditya?
Yeah.
Okay. I'll practice it offline with you after. But Aditya, tell me what are the first 3 that come to mind?
The 3 dimensions in space.
The translations. Translations, right? So if I had a point mass, like a marble, and I wasn't tracking its orientation, then 3 dimensions in which it can translate is sufficient. But the chalk can also rotate. So now we got into debate. What's your name?
Connor.
So Connor was saying maybe we have 6, and back there, someone said 5. Who's 5? What's your name? Anjan?
Yes.
Said 5. And so we have a little debate about just how many degrees of freedom do we need to record rotation. And I'm going to leave that debate until we come back and cover rigid body theory, so you can mull that over. And I'll formulate a simpler one for you to illustrate the principle, which is, what if this chalk lives in flatland? It lives on the plane. So the chalk can't go out of the plane. So it can turn and it can move around. How many degrees of freedom do you think the chalk has? So here is a configuration of the chalk. Here's another configuration of the chalk. Here's another. Here's another. It can move anywhere in flat land. So now what are your thoughts? How many? Let's do this by counting. Everyone must vote. Put up your hand when you believe the answer is right. I'm going to start. 0 degrees of freedom. 1 degree of freedom. 2 degrees of freedom. 3 degrees of freedom. 4 degrees of freedom. 5 degrees. Okay. So there were mostly 3s and some 4s, so let's pick on the 4s. So what are your thoughts on why there's 4 degrees of freedom?
Well, I can
Nice. So this brings up a really good point. So the answer was it can translate east-west or x direction. It can translate up and down, which is the y direction. And then it can rotate clockwise and counterclockwise. Any response to that? I have to get your name again. Oh, no, tell me. Abhijit. Yeah.
So if you consider clockwise and counterclockwise as two separate degrees of freedom, then positive x and negative x.
Okay, so Abhijit says to you that if going east and west are one direction, why is clockwise and counterclockwise two directions? It's a pretty good argument.
Yeah.
What's your name?
Justin?
Thank you, Justin. So that's a good argument. So we have to be consistent when we do this, right? So the way we'll be consistent about it is we'll just basically try to think locally at any one configuration. Does our space look like a 1D space, so a real number line? A 2D space, so does it look like a surface or a plane? Or does it look locally like a volume, a 3D space? And so I think in this case we can start to agree that if we have, this direction is x, this direction is y, we have a third direction, which is basically theta, how much we've rotated, right? And so rotating clockwise or counterclockwise is like moving positive or negative in theta. Does that make sense? Good. Well, as you can imagine, understanding what the configuration space is of that thing that you want to model is the first step. If you can't describe where it is, how can you describe anything else? But life would be very boring if I didn't move, right? So describing one configuration and ending there is not that interesting, right? And so the next thing we do is we say, OK, we have a configuration space. Let's say the two elevators. But now we want to describe the history of the motion or the trajectory. So for example, if I'm in this configuration space here, and I start at this configuration, and then I go this way to here, and this way to here, and this way to here, and this is my trajectory. Can someone take a stab at, can someone come up to the board? Can someone come up to the board? Come up to the board. Somebody better volunteer. I'm going to make the TA come up, and that's I get in trouble for that. What's your name?
Ray.
Ray, come on up, Ray. So Ray, you can use the class's help, but because sometimes you get blinded on the board. But the question here is, if this is the trajectory, and I give you two erasers, can you show us what the elevators are doing? So, yeah, show us what the elevators are doing. These two elevators.
Yeah.
So where do they start?
They start at the bottom.
At the bottom. OK. You could just the erasers will be the elevators. The erasers will be the elevators.
All right.
You don't have to draw. Just those are your elevators. Yeah.
So we start at the bottom,
Yeah.
and then at I'll call that T0, and at T1,
Yeah.
we have Q1 is halfway up, and then Q2 is still at 0.
OK. So let's see that.
Q1 is going to be, and Q0 stays, Q2 stays here,
Uh-huh.
so it doesn't make a noise.
Uh-huh.
And then moving from T1 to T2, Q1 stays the same, and then Q2 goes. So they're both halfway up now.
So now we're here, right?
Yep.
OK.
And then next, we can see that Q2 stays the same, but Q1 goes back down.
All right. Good. Very nice. Don't come. Stay here. Any questions about Ray's explanation here? If you're asked to plot the elevator's positions in the final exam, you'll know how to do it? All right. So now, what about this configuration? Not configuration, trajectory. And it keeps going round and round and round like this.
So let's call this T0.
Okay.
So at T0, Q1 is halfway up and Q2 is 0.
Okay.
And then a quarter of the way through, Q1 is going to be all the way up. And Q2 is halfway up. This is hard.
Yeah, it's hard. You can get help. But you were right. So, this is a quarter of the way, right?
Yeah.
So at this point, Q1 is all the way up and Q2 is halfway up.
But it looks like Q1 moves faster.
Really nice, really nice. Can you start explaining this to people?
So
Why don't you do the 4 positions first,
Okay.
and then we'll explain that part.
all right. So at T0, once again, Q1 is halfway up, and Q2 is at 0. And then at the first quarter of the loop, Q1's all the way up, and then Q2 is halfway up. And then halfway through, Q1 is halfway down, and Q2 is all the way up. And then at the third, fourth one, it's Q2 is halfway up, and then Q1 is 0.
Okay, so can you animate this?
Not at the same time.
Maybe maybe you have to do one and I have to do the other.
All right.
Where are we? Oh, this is going to be hard, right? Okay, I think we're ready. Ready?
All right. Yeah.
Wait. Let me make sure. Yeah. Okay.
Wait. If we start here, you're. Oh yeah, you're.
I'm at the bottom, right?
All right. Okay. Ready, set, go.
All right. So now, thank you. All right. High five. Okay. So now, no, you're not done. You're not done. So tell us about. Sorry about the chalk.
No.
Tell us about the velocity.
All right. So if you've taken trig, you can see that the value of Q1 is cosine, and the value of Q2 is sine. And if you know what a sine wave looks like,
So you're saying it's like Q1 is equal to like cos theta,
yeah,
or cosine of time, let's say,
yeah,
and Q2 is like sine of time.
yeah.
And if you plot this, you're saying you'll get this thing up to a sine.
You're going to get something that looks like this. I'm really bad at drawing.
It's pretty good.
Okay.
All right.
And so if this was a square, you would actually see them moving at constant rates, equal the same rate. But since it's a circle, it kind of slows down near the top and then speeds up when it's it's moving the fastest when it's halfway at the midway point.
Mm-hmm. And so that's exactly a good explanation. And another way to see that is if you're moving at unit speed along this circle, and you consider the shadow of where you are, drop down on here, then we're going to do this. Ray, you're going to draw the shadow as I move at unit speed. You're going to point to the shadow as I move at unit speed. Ready?
Yeah.
So you can see that when I'm moving vertically here, I'm not changing Q1 at all. The shadow's not moving. So it must slow down to a stop here smoothly before going in the other direction. Now show us the shadow for Q2. Yeah, your shadow's moving faster than me. This shadow is like, Right. So you can see that because of this tangential motion at the tops and bottoms, you're slowing down. So you can do it. If you know trig, you can write this out. And if you don't know trig, you can still see it just by the kind of slopes. All right. Now we're done with Ray. Thank you very much, Ray.